Welcome to the Problems Channel Season 3, Episode 2, the episode which I titled An Integral Transformation, because in this episode we will deal precisely with a way to transform one definite Riemann integral into another. But before we jump into the underlying mathematics, as a traditional and friendly reminder, if you're joining our channel mid-season, then first of all, thank you very much for your vote of confidence. Thank you for subscribing to our channel and welcome to our channel. And second of all, perhaps the most efficient way for you to gain the most academic benefit from working with the material that we present on this channel is for you to go to the home page of our channel, and at the top of that page in the channel's trailer section, find the episode titled The Problems Channel How To. Watch that episode in its entirety. We recommend that you follow all the instructions that we give in that episode, because in that episode we explain and motivate everything that we do on this channel. And if you have any questions, then by all means do ask. Find an episode that is of interest to you, use the comment section, and I will do my best in order to answer all of your questions. In the first problem of the third season, the mathematical problem S3M1, remember that with the letter M we designate all the problems in mathematics. S3M01, the letter M over here means that the upcoming problem will be the problem in mathematics. With the letter P we designate the problems in physics, and with the letter CS we designate the problems in computer science. As such, in the mathematical problem S3M1, we're asked to show that for all numbers theta and x real, such that the constraint here is important, the real numbers x are strictly greater than 1, and for all whole positive numbers n, which means numbers n vary as 1, 2, 3, 4, 5, 6, 7, and so on, it is the case that the definite Riemann integral taken between the boundaries of 0 and pi over the following integrand shown over here, x plus the trigonometric function of cosine evaluated at the angle theta times square root of x squared minus 1 raised to the nth power d theta. Over here it is important to realize that the integration is carried out not with respect to the traditional variable x, but with respect to the angle theta over here, theta, theta. And the definite Riemann integral shown on the left-hand side of the equal sign is equal to the definite Riemann integral evaluated between the boundaries of 0 and pi, where the integrand in this case looks as follows. 1 over x minus, this time it's minus. Over here on the left-hand side we have a plus. On the right-hand side we have a minus. The trigonometric function of cosine evaluated again at the angle theta multiplied by the same factor of square root of x squared minus 1, but this time this expression is raised to the power n plus 1. N plus 1 here, the degree to which this expression is raised by 1 higher than the degree into which the integrand raised on the left hand side, n versus n plus 1. And the integration is carried out with respect to the same variable theta. In the previous episode, and the episode Season 3, Episode 1, I have described and summarized all the problem-solving approaches that we have studied across Season 1 and Season 2, and I compared each and every individual problem-solving approach or a heuristic template with one musical note, and in some sense, across Season 1 and Season 2, we'll learn how to play one note at a time, but in reality, when we solve even more or less realistic problems in mathematics, theoretical physics, and computer science, it virtually never happens that just one problem-solving approach in a neat and beautiful way unlocks a solution of this or that problem. Usually, it is a combination of problem-solving approaches taken in a certain order, which really means a permutation of problem-solving approaches or a certain permutation of heuristic templates that unlocks a solution of even a modestly difficult problem in mathematics, physics, or computer science. And from now on, I will not be telling you guys which problem-solving approach you should use in order to solve the given problem in mathematics, physics, or computer science. That burden is on you. This is where you rise and shine and show your improvisational ability, your ingenuity and creativity in mathematics, physics, and computer science. And this is the whole point of working through the material that we present on this channel. And also, I will be from now on the problem statement. I will say a few words about the thumbnails to these episodes. I will try to show only the technical essence of the problem that we will be addressing in this episode. So the thumbnail to this episode does not say the words an integral transformation. It shows precisely the task that lies ahead. This is what we will cover, but evidently I cannot put these symbols into the string that is attached to the title of this episode. So this will be usually, if I can give a descriptive name for the formulas, then in the title of the episode there will be a descriptive string, but in the thumbnail, in the image, you will see the technical essence of the material that will be covered in this episode. And again, precisely because so far across seasons 1 and 2 we took our time to study each and every problem-solving approach in a dedicated manner. Usually I led you guys through a nicely cultivated garden path of, okay, here is a problem, and this is a problem-solving approach that will definitely solve it. Apply this approach to this problem and see how it works on the skills of applying, of understanding how this or that problem-solving approach works. But in reality, of course, the situation is much more different. Once we face a problem such as this one, for example, in real time, the process of solving this problem is usually a hot mess. It is ugly, it is awkward, it is not nice, it is nasty, and in the adrenaline rush to solve the given problem, we try this and fail, try that and fail, try something else and fail. Sometimes this is all we can do, fail, 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 and we can never solve the problem. Sometimes, yay, we can lock onto a successful approach and then unwind the solution of the problem all the way to the victorious. And in some sense, this is actually one of the most interesting parts of solving technical problems. The messy, the awkward, the ugly process of trying and failing. Once we find a successful solution, we sort of embellish it, beautify it, brush it up, and then we lay it out in a presentation that looks more or less smooth and coherent. And here is the thing. In this particular case, for example, the way I would solve this problem is basically an exercise in applying our favorite transform and conquer problem-solving approach. And the hint to that approach is in the title of this episode, an integral transformation. So a successful transformation of one integral into another unlocks a solution of this problem. And what kind of transformation do we do in this case? Well, the first thing that I would do, because a lot of times the fact that there is one and the same dumb integration variable on either side of the equal sign can be, sometimes it helps, sometimes it is not really helpful. So the first thing I would do in this problem is I will introduce the following substitution. I will leave the definite Riemann integral that sits on the left-hand side of the equal sign as is. Over here, I will massage the definite Riemann integral that sits on the right-hand side of the equal sign as follows. And you guys, once you understand what is going on, you're more than welcome to do it the other way. Leave the integral on the right-hand side as is and massage the integral on the left-hand side and see where it takes you. Do this experiment by all means. So on the right-hand side, in the definite Riemann integral shown over here, I would perform the following substitution. I will rename. In a sense, this substitution is quite straightforward, but look at the magic that it will allow us to pull. Let's say I will name that variable theta with some other name. Pick your favorite. Let's say I will pick the angle, let's say beta. So now theta becomes beta. And what does that mean? Well, if we take the first differentials of both sides, d theta equals d beta. So here the differential is transformed in a trivial way. And if theta is equal to 0, then beta is equal to 0. And when theta is equal to pi, then beta is equal to pi. Here, the transformation is very straightforward. So what we will have in the end is the following. On the right hand side, we will rewrite in your records. You guys do it, of course, with a new line and everything. Keep good track of what is going on. But here on the right hand side, instead of the angle theta, we now have the new integration variable beta, and our integral looks as follows. And again, in season 1, episode 2, I explained to you guys how to practice mathematics correctly. Do not listen to my presentation all the way non-stop without applying your own effort. Do apply your effort. Put this video on pause, walk away from the computer, and try to solve the problem completely correctly and on your own all the way. As soon as you catch the whiff of what is going on, so even now, use this as an opportunity to practice mathematics correctly. Put this video on pause and think, if you were to solve this problem this way, what would be your next maneuver? Remember that the intellectual or the mental habit of fixing a given problem in, let's say, mathematics or physics or computer science, and then trying to generate as many different enough or distinct enough solutions of that problem should be an integral part of the fabric of learning and doing mathematics. As such, if you come up with a different way to solve this problem, then please do not be shy. By all means, share your idea with our community in the comment section. Meanwhile, here is one successful maneuver. And the second substitution over here, in a sense, is to tie the angles theta and beta into the following relationship. The integrand that you basically saw on the left-hand side of our equality is x plus the trigonometric function of cosine evaluated at the angle theta times square root of x squared minus 1. It's not raised to any power higher than 1, just this expression by itself, times basically what we saw in the denominator of the integrand on the left-hand side of the equal sign, obviously with n plus 1 removed, only in the first power, x minus the trigonometric function of cosine evaluated at the angle beta times x squared minus 1. This product is equal to 1. Now, in general, it is highly unlikely, I do not think that you will be able to stumble or just happen to come up with this substitution or with this interaction between the variables theta and beta just by pure coincidence or by pure luck. You need quite a bit of an experience, but what speaks in favor of this particular substitution or this particular expression that ties the two variables together is the fact that overall in the integration business in general, what we have is at least 3 things going. Usually we have a evidently non-trivial integrand, that's number 1. Number 2, we have the differential d something. But now, because we have 2 interesting mathematical objects, an integral and the, let's say, first differential, then the third thing that happens and frequently works in our favor in symbolic integration, when that integration works and we can unwind the solution and integrate given integrand symbolically is the interaction. You see, it's the interaction between the integrand and the differential. Once we come up with some sort of substitution, not only do we change the integrand accordingly, we do not only transform the integrand, but we also transform the differential. And in that transformation, the material that pops out of the woodwork in terms of a new differential frequently interacts favorably with the transformed integrand, and that is how good things happen in the integration business. And here, in some sense, the other way to rewrite this expression is which way? Well, our integrand, almost integrand on the left-hand side equal to 1 over this animal right here, and this is almost what we have in some naive way, almost what we have in our definite Riemann integrals. Of course, there is one extra power in this guy, but again, if you have enough experience with working with definite Riemann integrals, you will know that sometimes this extra power precisely shows up when we lock the two objects or the two variables of interest in this particular relationship. And now we will see where this idea will take us next. And again, you guys should use this as an opportunity to put this video on pause, walk away, and try to solve this problem from this point onward completely correctly and on your own, and then compare your result to ours. Recall that in season 1, episode 1, in the first episode of this channel, I gave you guys a couple of definitions of mathematics, and even though this is not a definition, this is more of a description, but mathematics, among all other things, is a process. Nothing in mathematics happens instantly. Everything in mathematics happens over time, in the sense that we develop a solution, or develop what? Develop an idea. This is precisely the case in point. The time that we spend trying and failing, and then eventually honing on this relationship over here between the variables beta and theta is precisely constitutes the time when we were doing mathematics, the process of try and fail, generating new ideas, applying our voltage, intellectual voltage, creativity, ingenuity, and improvisational skills. Everything that happens after, depending on how strict you want to be, is either not mathematics with the capital case, or it is lesser mathematics, if you will. We can chalk it up to the computational calisthenics, if you will, because everything that will unfold right now is the result of an idea. So in mathematics, an idea is a first-class citizen, and mathematics is not symbolic shuffling. If anything else, mathematics is rearranging and shuffling ideas, generating and regenerating, and then combining and recombining ideas. Idea is the first-class citizen in mathematics, and symbolic shuffling and everything else that follows is subservient to it. So here we want to express the angle theta in terms of the angle beta and conversely, and first we will do the angle theta. So from the idea that is generated and captured symbolically over here, how do we express, let's say, just cosine of theta is fine. How do we express the cosine of theta? Well, the cosine of, let's say, I'll keep the same colors. The cosine of theta times square root of x squared minus 1 is equal to what? 1 over this animal right here, 1 over x minus cosine of beta this time, beta times square root of x squared minus 1 minus x. And what do we have? Let's carry out this computation together. Common denominator, 1 minus x squared plus x times cosine of beta times x squared minus 1, cosine of beta. And what is the denominator? We already agreed on it, x minus cosine of beta square root of x squared minus 1 beta. And what happens next? Well, next we observe that x, remember, x was strictly larger than 1. We had this constraint all along, so because of that, the square root is never 0. It is perfectly safe to divide both sides of this relation by one copy of the square root of x squared minus 1. And what do we see? Gone on the left-hand side. On the right-hand side, what do we have? Well, we have it here, gone. And what do we have here? Well, this is, again, nothing but middle school arithmetic. You see, computational calisthenics, not real mathematics. So the real mathematics was the intellectual voltage that took us to generate this idea. Everything else is lesser mathematics, if you will. So what do? It will be minus x squared minus 1, and this will be minus square root squared. Would you agree? Yes, you have no choice but to agree. This is middle school arithmetic, if you will. So when we cancel out one copy of the square root of x squared minus 1, so what do we get? Minus. Then there will be square root of x squared minus 1 squared. What will happen? The 2 will be gone. So 2 here is gone. So now what result do we have for the expression of the angle theta in terms of the angle beta? Well, that result is straightforward. Cosine of theta is equal to, let's write it down carefully, minus x squared minus 1 plus x times cosine of beta divided by x minus cosine of beta times square root of x squared minus 1 beta. Boom. There we have it. This is the result that expresses the angle theta in terms of the angle beta. And now we want to carry out the converse task and express the angle beta in terms of the angle theta. Spinning the above relation in the opposite direction, what will we have for the expression of the angle beta in terms of the angle theta? Well, let's carefully write that down also. The cosine, this time of the angle beta, cosine of the angle beta times, we're still working with this guy, times the square root of x squared minus 1 is equal to what? This animal right here is equal to 1 over this. We swap this guy and this guy with respect to the equal sign, rotate them over the equal sign, and what do we have? X minus this expression over here, 1 over this, right? So it will be x minus 1 over x plus cosine of theta square root of x squared minus 1. Here is the angle theta. Again, this is nothing but middle school arithmetic. There is nothing complicated over here. And overall, the material that we present over here, the task, is of a maybe upper high school variety. There is nothing complicated over here. A motivated high school student should be able to handle everything that we cover over here, with one tiny exception, that as a short and friendly quiz, see if you guys can recognize what do these definite Riemann integrals represent. And again, you either know or you do not. If you know, you will answer that question instantly. If you do not know, you will never answer it until you study enough mathematics. And I'll say a few words about the objects that these integrals represent at the end of this episode. So here we divided both sides of this equality by one copy of this. We obtained x minus this summand equal 1 over this guy, and then we rotated the summands that sit right next to the equal sign about the equal sign. X minus the reciprocal of this is here, equal to cosine times this, and that's how I wrote it. No magic. Let's write down the result. The result will be x squared plus x cosine of theta square root of x squared minus 1 divided by x plus cosine of theta times square root of x squared minus 1. This time we're working with the angle theta. Angle theta, again, middle school arithmetic. There's nothing complicated over here. Because x is strictly larger than 1, this expression over here never 0. Divide by this on the left-hand side of the equal sign. Divide by the same thing on the right-hand side. And what do we have? Well, we now have this guy right here. This is the guy. See, this is it. Again, x squared minus 1 is represented as what? As the square root of the whole thing squared. Once we extract the square, what do we get? Well, we have the square root of x squared minus 1 left over here once we do this cancellation, and we right away write down the result for the cosine of the angle beta expressed as the function of the angle theta. What will it be? Let us write this down. Square root of x squared minus 1 plus x times the cosine of the angle theta divided by x plus cosine of the angle theta times square root of x squared minus 1. And this time we have the angle theta. And voila, this is our result, which expresses the angle beta, or technically, pedantically, the cosine of the angle beta in terms of the angle theta, or in terms of the values of the trigonometric function of cosine evaluated at the angle theta. And now that we have these two expressions on the books, we want to see the boundaries within which the angles theta and beta vary. Now that we manufactured two expressions for the trigonometric function of cosine, which over the set of all real numbers varies between 1, positive 1, and negative 1 inclusively, we better show that it is the case and that they by absolute value, our expressions shown on the left and on the right do vary between, by absolute value, they are less than or equal to 1. We will do that in a few seconds, but first we want to establish the boundaries for the angles beta and for the angle theta. So in this case, first let us consider what will happen if the angle theta is equal to 0. What will happen in this case? Well, in this case we will have square root of x squared minus 1 plus x, because the cosine of 0 is 1. Here the cosine of 0 is 1. We'll have x plus basically the same expression. The real numbers commute under addition. So what do we have? We have that the cosine, we have the cosine of the angle beta in this case is equal to 1, which implies what? The angle beta is also, well, on a given, obviously, the trigonometric function of cosine over the entire real number takes on the value of 1 infinitely many times over all the integral values of y that are even, multiples of 2. So we take the smallest one, the first one here, beta is equal to 0, that much we see. And what happens if the angle of theta, let's say theta, is equal to pi? Because remember, our integral on the left-hand side in the original problem, the angle theta varies from 0 to pi. So when theta is equal to pi, what do we have? Well, when theta is pi, then the cosine of pi is -1. So what do we have? We will have in the numerator square root of x squared minus 1 minus x divided by what? X minus square root of the whole thing. X squared minus 1. So here's a short quiz for you. What is the value of this expression? Let's say factor -1 over here. So this will be minus x minus square root of x squared minus 1 divided by x minus square root x squared minus 1 is equal to -1. -1. Again, the trigonometric function of cosine over the set of all the real numbers takes on the value of -1 infinitely many times over all the integral multiples of pi that are what? That are odd. But we take the first one. So in this case, we claim so that beta in this case will be pi, because this will be expression what? For the cosine of the angle beta. This is the expression for the angle beta. You see, so the cosine of the angle beta is equal to -1. So beta is equal to pi. And conversely, according to the formula shown over here, if the value of the angle beta is equal to 0, what will we have for the value of the trigonometric function of cosine evaluated at the angle theta? Negative square root of x squared minus 1 plus x, and that will be in the numerator. In the denominator, we will have cosine of 0 is 1. Again, x, same way, minus square root of x squared minus 1. So that value is 1. Then the cosine of theta is equal to +1 cosine of theta. Again, out of the infinitude of even integral multiples of pi, we choose the most convenient one in a sense. That means that theta is equal to 0 as a sanity check, and if the value of the angle beta is equal to pi, we take from here beta pi. So then what will we have for the value of the trigonometric function of cosine evaluated at the angle theta? What will happen? We will have negative square root of x squared minus 1 minus x divided by x plus square root of x squared minus 1. We factor out -1 here for both summons and the numerator. We'll get the same expression in the denominator as in the denominator, modulo the multiplicative constant -1. So that will be -1 multitude, add multiple integral multiples of pi. We choose the most convenient one. So theta, this implies that theta is equal to pi. See, so now not only we showed with our intuitive substitution of theta equal to beta, but with this here clever expression between the angles theta and beta, we also proved that the boundaries of integration indeed remain the same. And now we have a good reason to suspect that not only our cosines of theta and cosine of beta take on the values of +1, -1 in either case, implying that the corresponding angles take on the values of 0 and pi. We also have a reason to suspect that these trigonometric functions, these expressions, by absolute value, we want to show, for example, that the absolute value of cosine of each angle is less than 1. We'll say theta and beta. I will jam everything into one expression, but that's the idea. And this will show that the angles theta and beta do vary between 0 and pi, as our calculations suggest. We now want to show that the expression that we obtained for the value of the trigonometric function of cosine evaluated at the angle theta is indeed by absolute value is less than or equal to 1. And we will start, let's say, with the right hand side. We first want to show that this here expression is less than or equal to 1. Again, it can be shown in a multitude of ways. Perhaps you can invent a clever highbrow Jensen inequality, Olympic style inequality somehow, or any other inequality, but I will choose the most straightforward route. I will work with middle school arithmetic and show how can we unwind this inequality into something that is definitely true. And then for a polished presentation, when you will be presenting your solution and your work, you will retrace your steps in reverse order and follow and present your results shown over here the way the people expect it. So one way to proceed here is as follows. Let's say if we carefully graph the functions of interest over here, let's see, this will be our, let's say this is x, then the graph of the function y equal to x, let's pretend that this is the graph of this function y equal to x. Then let's use some sort of orange. So let's pretend this is 1 and let's pretend this is -1. So this function over here, square root of x squared minus 1, because x is squared, right, it will always be in the upper half plane, so it will run as follows, and then y equals x will be the asymptote for these values of real numbers x. But on the negative side, the branch will run symmetrical for this branch with respect to the y-axis, but it will run somehow this way. So that tells us, because x is strictly larger than 1, that in this area of interest, the function x is always greater than square root of x squared minus 1. We multiply this guy by something that is definitely, we think, is also less than or equal to 1. So regardless of the value of the trigonometric function of cosine evaluated at the angle beta, positive or negative, this expression shown over here will remain strictly positive. So this will be, let me write it down, x squared minus 1. These are two branches, this guy and this guy. You see, so this is the area of interest for us. So things look favorable for us. So what do we have? We multiply both sides of this inequality by a strictly positive quantity shown over here. And what do we have? Well, on the left-hand side, we will have negative square root of x squared minus 1 plus x times cosine of the angle beta. Less than x, what do we have there, minus cosine of the angle beta times square root of x squared minus 1 angle beta. And now we want to bunch up the like terms on the same side of the inequality sign. So we will move this suspect over here, and we will move this suspect over here. And in this case, what will happen? Well, the one copy of, will go like this, square root of x squared minus 1. It will be cosine of beta minus 1. This will be cosine of beta, right? Because this summand is with the negative sign. And then less than or equal to x of what? 1 minus cosine of beta. You see, this is what's happening. Now we factor this minus sign out, and then in this case we will have 1 minus cosine of beta and 1 minus cosine of beta. what happens over here. We need to be careful when the cosine is equal to 1, but when it's not, we can cancel these guys out. And here there will be what left with the minus x squared minus 1 less than or equal to x. This is what we will have, and this is definitely the case. When for the positive values, when we drop them in, what will happen over here, this thing will look on the graph, you will see the same values but taken in the negative direction. They will go which way? They will go this way. Which way they will go? They will go this way. And if we square both sides of this relation, we will have x squared minus 1 less than or equal to x squared. X is a real number. In our case, it's greater than 1, but that is the case of what? Minus 1 less than or equal to 0. And then once we see that this is true, we unwind our steps for the final presentation. When we show the result to someone else, we start with an obvious, with a true statement. We add the square of a real number. We observe that this is true. Why? Because remember, x in our case is always greater than 1. X is always greater than 1. And then we add more and more things, reshuffle, and we show that this part is certainly true. And now we want to show that this expression is greater than or equal to -1. We next want to show that our expression for the trigonometric function of cosine evaluated at the angle theta that we manufactured over here is larger than or equal to -1 as shown over here. And don't forget that all along as we work, our area of interest for the parameter x is this band right here for the real numbers, x strictly larger than 1. So we can even puncture this guy out, and this is our area of interest. So that's why when in the previous segment we had negative square root of x minus 1, this branch is always less than the area of interest x. So here we do the same thing. We take our denominator, we multiply both sides of inequality by 1 and the same strictly positive real number, and what do we get? We have negative x plus cosine of beta times the square root of x minus 1 less than negative square root of x squared minus 1 plus x times cosine of the angle beta here and beta here. And again, the drill is the same. We group like terms on either side of the inequality sign. We move this suspect over here and we move this suspect over here. Once we do the grouping, once we switch the terms and we factor out the common term, what will we have? On the left hand side, we will have square root of x squared minus 1 times, this was minus, it became plus, 1 plus cosine of beta, presumably less than or equal to x, factor out, also 1 plus cosine of beta. Again, going back to middle school, we cannot divide by 0. Can anything over here be 0? Yes, when beta is equal to pi, cosine of pi is -1. Positive 1 and -1 is 0. We have 0, we cannot divide. But then what do we have for a fixed value of x? We have 0 times 0 on the other side. 0 is less than or equal to 0. This is a true statement. So when beta is not pi, then it is legal to divide. You have to carry out all this analysis, say all these words, and then what do we have? Square root of x squared minus 1 is less than x. Again, this is our classical situation over here. It is always the case. Square both sides. X squared minus 1 less than x squared, and then one and the same strictly positive real number. -1 is less than or equal to 0. This is a true statement. So now that you understand how things work in reverse order, you do the presentation, and perhaps someone who will be reading your reasoning will think, gee, where did this come from? Well, this is where did it come from. Start from here, move here, move here, say the right words, introduce these things, and unwind them back into this. So now what did we show? We showed that the absolute value of the trigonometric function of cosine of angle theta, which color did I use? Red. Theta is less than or equal to 1, and now we will do the same thing for the angle beta. We want to essentially go through the same exercise for the values of the trigonometric function of cosine evaluated at the angle beta, where we obtained that expression in the previous segments, and we want to show that by absolute value it is less than or equal to 1. The same ideas apply. Here, again, regardless of the value of the trigonometric function of cosine evaluated at the angle of theta, remember that the angle theta varies between 0 and pi, and the cosine in this case runs which way? From +1 to -1, like so. This is pi, this is pi over 2. This is our cosine. It changes the sign, but even if cosine of theta is negative, we still have this situation here. So when we multiply both sides of this inequality by one and the same positive quantity, this sign doesn't change. So what do we have? Square root of x squared minus 1 on the left hand side plus x times the cosine of theta. Cosine of theta is presumably less than or equal to x plus cosine of theta times the square root of x squared minus 1. You know the drill. We move the square root of x squared plus 1, let's say, to the left. We move the term with x to the right, factor out x squared minus 1. What do we have? 1 minus cosine of theta, presumably less than x. Also 1 minus cosine of theta. Can either side be equal to 0? Yes, sure. Why not? When theta is 0, then cosine is 1. 1 minus 1 is 0. But then for a fixed number x, we have 0 times the real number is less than or equal to 0 times a fixed real number. True statement. When theta is not 0, then the expression in the parentheses cannot be 0. It is safe to cancel out. And what do we have again? Square root of x squared minus 1 less than or x. Square both sides. X squared minus 1 less than or equal to x squared, or -1 less than or equal to 0. This is a true statement. Again, for a polished presentation in reverse order, we roll up the steps, we say the right words, and we introduce magically all these expressions, and we fold it into this here expression, and we show that it is less than or equal to 1. And now we do the same thing with -1. We now want to show that the expression written down over here, this is basically our cosine of the angle beta, is greater than or equal to -1, as shown over here. We want to work with this with the left, so to speak, side of this inequality. Again, our area of interest for x, when x is a particular real number, is shown over here, strictly larger than 1. And the drill is the same. We take this inequality, multiply both sides of it by 1 and the same strictly positive real number. And what do we have? We have negative x minus cosine of theta times the square root of x squared minus 1. This is the angle theta, which is presumably less than or equal to square root of x squared minus 1 plus x times the cosine of angle theta. The idea here is the same, to bunch up the like terms on the same side of the inequality sign. Let's say we move x to the left and we move the square root to the right of our presumed inequality sign. What do we have? Plus x jumps over to the left, becomes negative x, factor out negative x, obtain 1 plus cosine of theta in parentheses, presumably less than or equal to square root of x squared minus 1. Again, negative sign over here, jump over, gain plus 1 plus cosine of the angle theta. Can anything over here be 0? Yes, all day long. When theta is equal to pi, cosine of pi is negative 1. Negative 1 plus 1 is 0, but then we have for any fixed real number x, something times 0 is 0. Same thing on the left hand side, and 0 is less than or equal to 0. Certainly true. When theta is not pi, it is safe to divide both sides by 1 and the same real number here in this case. And then what happens? We have negative x less than or equal to square root of x squared minus 1. We multiply both sides of this inequality by negative 1. By doing so, we need to flip the sign. X is greater than or equal to negative square root of x squared minus 1. Is that true? Well, remember our area of interest over here. Our of interest right here with 1 punctured out. Here, this is the guy. So in this case, the partial graph of this function will run which way? It will run symmetrically, but somehow this way. And for us, for x equal greater than or equal to 1, somewhere here, these are our areas of interest right here. Definitely at any point, this is definitely larger than anything that this branch has to offer. This is certainly true. So what do we have now? We square both sides. X squared greater than x squared negative 1, and then 0 is greater than or equal to negative 1. Certainly true. Now for a polished presentation, for someone who will be refereeing or arbitrating your work, start from here, move here, move here. Say the right words over here because x strictly larger than 1. Introduce the magic cosine of theta, unwind it, and show it folded into this inequality. And evidently partial graphs are never a proof, but as a visual candy for a few fixed values of x, such as 2, 3, 4, and 5, here is what a partial graph of the cosine of theta looks like in terms of cosine of beta. And conversely, for several fixed values of the real number x, such as x equal to 2, 3, 4, 5, for example, here is a partial graph of the trigonometric function of cosine of beta in terms of the trigonometric function of cosine of theta. And inhaling the last two segments, what we managed to show is that by absolute value, the value of the trigonometric function of cosine of what? Of beta. Beta here is less than or equal to 1. And now we have set up our groundwork. We did the necessary preparations and we can move further. Back in season 1, episode 1, I gave you guys two definitions of mathematics, and according to one of these definitions, mathematics first and foremost is an art. It is no different from, let's say, visual arts or literary arts. It has its own specificity, of course, but after you do mathematics for, let's say, 10, 15, 20 years, eventually, hopefully, you will see the light and you will realize, yes, mathematics is an art form, and drawing this parallel, you should be able, ideally and hopefully right away, give me the two names that I'm looking for right now. Who is the person whose portrait you saw a few seconds ago, number one, question 1, and question 2, who painted that portrait? And if you ever did any sort of painting, especially oil on canvas, you know that before you touch the canvas with a brush loaded with your paint, you have to do actually fair amount of preparatory work. You have to stretch your canvas, you have to ground it, you have to lay out your palette, squeeze the paints, mix them up maybe a little bit, pull out your brushes, pull up your apron, and on and on and on. And the work that we have done in the previous segments is, yes, it is boring, but it is mandatory. Unfortunately, many students do not really do it. But now that we prepared the canvas, we are ready to paint. Our canvas has been grounded, our paints, our colors have been squeezed out, our brushes are prepared. We're now ready to have cosine. We're now ready to have some fun. And at this point, x squared minus 1. And what do we have here? Here we have our angle theta, right? And here we have our angle beta, and here we have our angle beta. I think I got that result right. Keep me honest if I did not. Again, I apologize for any typos that I make. I may say one thing, I mean totally the other. Sometimes the brain does not connect with the tongue. I may write something not the right way also. Apologize again. But now the point is this: we have prepared our canvas. It is ready to go. What do you think your next step would be here? Again, if you are tagging along, here is an opportunity for you to put this video on pause, walk away, think on your own, try to carry this idea in this computation through all the way correctly and on your own, and compare your result to ours. Computing the first differential of both sides of our relation that we deduced in the previous segment, we obtain the following. The first derivative of cosine is minus sine of, let's say, theta, and then d theta. And then on the right-hand side, what do we have? The first differential of this animal will be negative x sine of beta times x minus cosine of beta times the square root of x squared minus 1. minus beta and beta, then minus our expression over here, negative square root of x squared negative minus 1 plus x cosine of beta times the first differential of this animal right here, but the first derivative of cosine again is minus sine, minus times minus is a plus. So what will we have? We will have the sine of beta here times the square root, I'll leave it like that, divided by what? This is u over v squared, so x minus cosine of beta square root of x squared minus 1 squared cosine of beta. You see, and over here we have d beta, our first differential, and here I have, it's a little bit too small for you guys, but you understand what is going on here. There's nothing complicated over here. We computed the first derivative and the differential of the function that looks like u over v. If we take that's u prime v minus u v prime over v squared, and then we take the differentials, there is no magic over here. This is a trivial exercise in computing first derivatives. Now, let's work carefully with these signs. Multiply both sides of this result by -1, get what? Plus. We get plus over here. Everything is nice. And now we witness what? X, we open up the parentheses on the left summand. We get what? Here on that side, we get x squared times the sine of beta, of the angle beta. Would you agree? X sine beta times x squared. Then we have the minus sign over here, so we have minus x square root of x squared minus 1 times the sine times the cosine, and both times the angle beta figures over here. Beta, you see, again, nothing fancy going on. So here we have negative square root of x squared minus 1 times this expression with this here square root also. So we have what? Minus x squared minus 1 times the sine of beta, and plus x square root of x squared minus 1 times again sine and times the cosine of beta both times. This is again mundane arithmetic. This is not what it took to come up with this, but we just carefully do the arithmetic over here. So what do we see? If we unwind this nasty term over here, we will have what? Minus x squared sine of beta, negative minus sine plus the sine of beta. You see, again, nothing complicated. And now let's witness the magic. This term and this term cancel each other out. Now this horrible animal over here, sine, cosine, x, and square root with a negative sign. And here what do we have? X, square root, sine, cosine with a positive sign. Cancel out. And what do we have left? Amazingly enough, what survives? The only thing that survives is this sine of beta. From all this horrible string of symbols, the only thing that survives is the sine of beta. And now that you guys understood where all this came from, again, this is literally beyond taking the first differential of the ratio of two functions. Everything else that followed was really middle school arithmetic. So now let me erase, once you understand where this manipulation came from, let me erase this and write down the result that you should name. And I will also erase here. Again, nothing complicated. Rewind or ask questions if you miss something. I will leave it like that just for the neatness of the presentation. And what do we have here? In the result, we have here the following result. The trigonometric function of sine evaluated at the angle beta over x minus cosine of beta times this squared d, that's the first differential of beta. So far so good. Again, nothing complicated. We just took the first differential of both sides of these two, both sides of this expression, here and here. Derivative of u over v, arithmetic. Happy cancellations ensued, and this is the result that we have. The sine of theta d theta is representable as sine of beta over this expression d beta. So far so good. Now again, put this video on pause, walk away, think on your own. What would be your next maneuver if you were to solve this problem in that way on your own? Now, in general, for the sine of any angle, let's do it this way. The sine of theta, let's say, theta is equal to what in general? It is equal to plus or minus square root of 1 minus cosine square of the same argument. That much we know. This is true in general case. But remember, what we're dealing with is the situation when 1 minus 1, let's say this is pi over 2, somehow this is pi, this is horribly not to scale. This is the cosine, and what is the sine? The sine goes this way, so the sine is what? The sine is positive, so in this case between two signs we choose which one? Exactly, the plus sign. So now we compute this here animal in terms of this expression that we have. That's all we do. Again, it's middle school arithmetic. That's the program. And when we do that, what will happen? Well, all we have to do is this. Let's hijack this expression and write it down like this. 1 minus cosine square will be equal to what? Let's jam it in. 1 minus this scary thing squared. This is all there is to it. And again, common denominator, this guy will be squared. We move it over here, and you should be able to carry this computation through on your own, but for the benefit of everyone, let's do this together. So what will we have? Here we will have the square, x squared minus 2x cosine of beta square root of x squared minus 1 plus, let's say here we will put this guy in front, x squared minus 1 times cosine square. This is the square of this term, cosine square of beta minus this whole thing minus square of this expression. So here the square of this term over here is basically the expression under the square root, you see, and we have a minus over here. This is minus, so here will be minus x squared minus 1. Here we have minus, so minus twice the product between this term and this term, but we have minus here, so minus becomes a plus. So plus 2x cosine square root of x squared minus 1. here we have beta still. Keep me honest and verify. And what is the last thing? Minus the square of this guy. So it will be minus x squared, and what do we have? Cosine squared of beta. Cosine square of beta. And all this beautiful mess must be divided what? Must be divided by the square of the denominator. X minus cosine of beta, x squared minus 1 squared, and here we have angle beta. Now let's go to work. Minus 2x cosine beta square root plus 2x cosine beta square root. So this and this cancels out. So here we have x square cosine square of beta and negative cosine square, x square cosine square. So this cancels out with this over here. And what else do we have here? We open up this guy, negative x squared and positive x squared. So we cancel out here and cancel out over here, negative square. And what do we have left? So we have negative sign and negative sign 1, and we have 1 in front of the cosine. So we here, as a result, once you unwind, you will have 1 minus cosine squared of beta. Look at this wonderful, as if by magic, step. And what is this? Exactly, this is the square of the sine of beta. See, the sine of beta shows up again. But this is a square and this is a square. So when we take the square root of all this beautiful work that we have done, what will survive as the result of this? Well, let's write it down. We can even be brave and erase this material. Let's erase this material right here. We will erase this material, and we will write that the square root of this will be equal to what? Sine of beta divided by x minus cosine of beta times the square root of x squared minus 1 cosine of beta. And remember this, remember our reasoning. We took the square root with the plus sign, and that, with our variance of material, is equal to precisely what? It is equal to precisely of sine of theta this time. Sine of theta. And this is the result that we were gunning for. This is what we're after. So now we'll start combining the results that we accumulated so far, and in the next segment we will use this result and the result which we obtained by differentiating both sides of the expression for the cosine. Remember, we differentiated, we took the first differential of this side with respect to theta, angle theta, and we took the first differential of the right hand side with respect to the angle beta. Remember, we had d beta. So now we bring this guy into here, and this is what will happen. Next, we take the result that we developed in the previous segment and the result that we developed in the segment prior to that, and we simply merge them together. In other words, into the left-hand side of the previous segment, the result that we developed there, we inject the right-hand side for the image of the value of the trigonometric function of sine evaluated at the angle theta. In plain English, we take basically this expression over here and slug it over here. That's it. That's all we do. So in other words, we write over here d, let's say, now that you guys understand what is going on, we write d theta, and then we equate this result to this result. In other words, this is the same thing as this. That is all there is to it. To the right of the sine of theta, we attach d theta, this guy. We can even go this way. But now through this result, this is what we have. And what happens next? Well, look at this. Sine of beta and sine of beta cancel each other out. Wonderful. And here, one copy of the denominator. Well, let's do it with 2. And here is one copy is gone. That's it. Is it wonderful? It's absolutely wonderful. What do we have now? Let's write down the result. D theta for the first differentials, and this is the material that goes into our integrands for the d theta. What do we have? We have d beta, that's the first differential of the angle beta, divided by what? One copy of this animal right here, x minus cosine of beta times square root of x squared minus 1. We put the angle beta over here. We all witnessed how all these results were developed, and we're pretty much home free. What we have to do now is take our clever relationship over here, write down that this is equal to 1 over this, bring in the differentials. That's the result that we developed, and we proved that it is correct, and we're done. And perhaps the thing I forgot to tell you guys is that when we proved that our trigonometric functions, remember the cosine of both angles, we had beta and we had theta. Through the results, through this relationship where we wrote down explicitly the shape of cosine of theta in terms of cosine of beta, and conversely, the shape of the cosine of beta in terms of cosine of theta, we said that the angles here themselves vary between, between pi and 0. Both angles themselves vary, theta and pi. What does that mean? Well, through all these graphs, you basically saw we have to say that for every value of the real number theta within the subset of real numbers between 0 and pi, there corresponds a particular real number beta from the same subset of real numbers, and conversely, for every real number beta from the subset of real numbers 0 to pi, there corresponds a particular, through the other formula that you saw for the cosine of beta, the other particular value of the angle of theta that belongs to the same subset of real numbers. So now all the manipulations are legitimate, and the last mile, the last step, when we bring the differentials into this here expression, it will look as follows. We now go back to the expression, to our original expression that binds the two cosines together into this beautiful relation. And I use yellow chalk. Let me use yellow again. I'm already running out of yellow, but so what do? We express the left factor in this expression through the right one. So what do we get? We get, let's see, probably this is a good, x plus the cosine of the angle theta, see theta, times the square root of x squared minus 1. Through this relationship, it is equal to, I will leave the room, you know why I will leave the room here, x minus cosine of beta square root of x squared minus 1. I will put the whole thing in parentheses, and you already see what is about to transpire here. Except that should be 1 over. Yes, 1 over. We simply move this under the positive unity. Now what do? We raise both sides of this relation to the same whole positive power n. 1 to the n is 1, and this is n. So far so good. So far so good. Now we take this result and we multiply this result by this one through. So what do we get? We get d theta. D theta is equal to what? This will be 1 times d, let me use yellow to be consistent, d beta, but we have one copy of x minus, which is this guy, so we add plus 1. So far so good, so far so good. Now we integrate both sides. We integrate both sides over the same boundaries, 0 to pi, 0 to pi. This is why we did all the legwork prior. And what do we have? We basically have almost our original expression. Now it's just a cosmetic step. Here we rename beta. We rename beta into theta, and voila, we have the result that we were required to prove. And again, you either know these things or you do not know these things. If you do not know them, you will never answer the question correctly, but if you do, you will answer this question instantly. Modulo the multiplicative constant, if I'm not wrong, that must be that multiplicative constant must be pi, if I'm not mistaken. For the specialists, keep me honest, I think it is pi. But the integrals over here with the pi in front is the representation of the so-called Legendre polynomial. So I think that's how these things are spelled. Of course, this will be P of n. P of n. Legendre polynomials, these are the guys. These are usually represented as or introduced as the solutions of a certain differential equation of order 2, but for us it's not really that important. What the important part was to show how in the more or less grown-up environment, realistically academic in an academic setting, the transform and conquer, in this case, the problem-solving approach, that was the first one that we studied, transform and conquer. Again, if you missed this whole thing completely, you joined our channel later on. We recommend that you go back and you watch season 1 and season 2 altogether. I think season 2 is 55 episodes, 2 episodes for the introduction in season 1, and 7 meaty ones, 55 and 762, about 62 episodes you have to work through if you joined our channel too late, but hopefully you will not regret. You will catch up to what is going on, how these things work, and you will understand how the transform and conquer problem solving approach works. But now this is it for the mathematical problem S3E2, and we will move on to a new challenge next. Originally, I wanted to turn this into just one problem, but then I realized that even for our channel, that will be too much for one episode, even though I can glom everything into one episode and make it a really long one. But I decided to take it easier on myself and on you guys, and I will split it into 3 problems and 3 episodes. And now we will be taking on with full frontal interaction, so to speak, the idea that the intellectual habit of fixing a problem, and then let's say we represent this point with the problem, and then finding as many different distinct solutions of such a problem as possible. That idea, that intellectual habit of doing this should be an integral part of the fabric of studying and doing mathematics. This is how you develop your ability to improvise, show your ingenuity and creativity. One way is not enough, so to speak. Ideally, you want to have many different ways to solve one and the same problem, and usually that can be done quite often, especially initially in an academic setting, depending, of course, on the machinery. Certain problems can be solved with a machinery that most students could not possibly follow. So here, I will split the next challenge into three. It will be three problems in mathematics. After that, we'll solve a beautiful problem in physics. But here, the next challenge will consist of three problems: S3MO2, MO3, MO4, all basically related to one, and the idea is the same. Take this finite sum, the sum of, hopefully you guys can see that well enough at this point, k, 0, and the sum of the values of the trigonometric function of cosine, evaluated at the following argument: a plus k times theta. What is it? Can you invent, develop, synthesize, construct, discover a synonym for this here finite sum? I captured the constraints over here. A is a constant real number, n is a positive. Well, if we take 0, let's say, is a non-negative whole number. It can run 0, 1, 2, 3, 4, 5, 6, 7, and so on. And what we're looking for is at least three distinct deductions of what is the synonym for this here expression. Again, in the big scope of things, actually these things come in quite handy. For example, the result that we will develop can be and frequently used in, for example, integration. In the tactical maneuvering with Riemann integrals, this result will be quite helpful. But again, overall, the intellectual habit of fixing a problem and constructing as many distinct enough solutions to the problem should be an integral part of the education of studying and doing mathematics, and we will come to that concept face to face across the next 3 episodes. And for this episode, this is it. Thank you very much for watching. Thank you for your time. I will see you in the next 3 episodes, in which I will present and share my 3 distinct deductions or 3 distinct solutions of the mathematical problems S3, M2, 3, and 4.